Hi, everyone. Welcome. Thank you to everyone in the audience as well as everyone online for joining us today to hear this wonderful lecture put on by the Keck Institute for Space Studies. Today's talk is titled NISAR, the Next Phase in Remote Sensing of the Earth, Earthquakes, Volcanoes, Aquifers, Glaciers, and Devastation, given by Dr. Mark Simons. Dr. Simons is the chief scientist at JPL, and he's also a professor of geophysics here at Caltech in the Seismological Laboratory within the Division of Geological and Planetary Sciences. As the chief scientist at JPL, he's responsible for the leadership of the scientific and research community, and he serves as the focal point for interactions between JPL and the external research community. He received his bachelor's in geophysics and space physics from UCLA in 1989 and his PhD in geophysics from MIT in 1996. He joined Caltech as a postdoc after that, and he's been a professor here ever since. His first experience at JPL was back in 1990 as a graduate student, working with gravity data and SAR imagery data of Venus from the Magellan mission. Since then, his research has focused on advancing the ability of space geodesy, using technologies such as Interferometry Synthetic Aperture Radar and global navigation satellite systems to measure deformations of Earth's surface. Dr. Simons' research uses observations to study geophysical processes, ranging all the way from earthquakes, volcanoes, landslides, glaciers, to tectonics of terrestrial planets and other ocean worlds within our solar system. A fun fact about him is that he's been a backcountry skier for over 40 years. In addition to studying the Earth, though, he also gets his hands dirty in his orchard, where he impressively grows everything from avocados to pomegranates to oranges and many more kinds of citrus. I'm sure we're all very excited to hear Dr. Simons talk today and what he has in store for us, so please help me in welcoming him to the stage.
Well, thank you. With that introduction, I guess we can go home now. It is wonderful to be here. Thank you to KISS for the invitation. Several of us in the community have waited 30 years for this mission. In fact, when I started at JPL 30 years ago, I was told you would have a SAR mission in 3 years. So within an order of magnitude, we're doing fine. So this is an extraordinary mission. I'm going to talk about NISAR, and I'll tell you a little bit about what NISAR is in a second. But I just want to point out that all these kinds of efforts are done only on the backs of huge teams. And in this case, it's both here in the US and in India. All of you who are on the NISAR team who are in the room, can you raise your hands, please? All right, so they're going to hold me accountable if I say anything stupid, or they're going to interrupt and correct me, as they are wont to do. All right, so let's go. We have a lot to cover in a short amount of time. Let's cover the basics, because NASA is the world of acronyms and acronyms of acronyms. So I want you to understand that NISAR is the NASA-ISRO SAR mission. NASA you probably recognize. ISRO is the Indian Space Research Organization, and SAR is Synthetic Aperture Radar. Don't confuse NISAR with INSAR, same letters, different order. Which stands for Interferometric Synthetic Aperture Radar, and this is what we're going to focus a lot on in the slides to come. All right, so my plan for today is really first to tell you a little bit about what NISAR is. I'm going to give you the quickest and briefest primer on what our measurement is to give you a feeling of what it measures and how it works. And then we're going to give you 3 different classes of applications, all taken from geophysics, because that's what I do, at the expense of all the other things that NISAR does. And then I'm going to end with sort of a contrast into these vignettes all being derived from existing data, why we're so excited from NISAR and the kinds of data it will give us relative to what already exists. So NISAR is a radar satellite, and before getting into any details, I do want to remind people a little bit about what we mean with radar. So here's the electromagnetic spectrum that many people are used to looking at in their spare time. Here is the visible that we are used to looking at in our daily lives, and sort of looking at frequency and wavelength. We're going down much longer wavelength, lower frequency to look at radar waves, like the waves that you have using your cell phone and your microwave. What's important, though, isn't the kind of imaging that we do of the Earth if you look at Google Earth or other kinds of optical imagery, you're typically used to looking at reflected light from the sun. So the sun is your flashlight. It's shining on the Earth, and you're taking a picture of the Earth at different parts of the spectrum here. Sometimes we look at emitted radiation from bodies. Typically in the thermal infrared, it's very common. Radar is a class of active remote sensing as opposed to passive. So we're bringing along our own flashlight. We're actually illuminating the ground with a radar, and then using the same instrument to actually look at the reflected light from the ground. Okay? So that's a fundamental difference, and it's one of the reasons that radar satellites are typically very big, because you have to have enough energy to actually radiate the Earth and get the reflection back. We're going to talk about radar frequencies frequently, and I will slip and I will use a shorthand that talks about these bands, L, S, C, and X, which is totally nonsensical, but it does refer to different wavelengths. And a lot of the examples, but not all I'm going to show you, are from short wavelength radar, sort of typical centimeters, a few centimeters in wavelength. Whereas as we go to NISAR, it's typically longer wavelengths in the sort of 15 to 30 centimeter wavelength range. And you'll talk about why that's important in a second. One of the important things with radar, as opposed to optical imagery, is that it sees through clouds and it sees at night. So we don't care if it's daytime or if it's nighttime, if it's cloudy. And that's very important. That means we can image the entire Earth all the time from an orbiting satellite, and we don't really care about the weather. It doesn't mean that there are not effects from the clouds, and we'll talk about that potentially, but it doesn't stop us from making measurements. So this is the NISAR satellite as we expect it to look next year. And for our purposes, what matters, you have the solar panels here, and you have the SAR radiating elements here. They radiate upwards on this big reflecting antenna to the ground. It scatters and bounces off the ground, comes back up, reflects off of this, and back onto the instrument. That's all you need to know. The rest of it is details. So NISAR, typically if you're interested in planetary missions, we send up these big satellites, and they're like Christmas trees. They have like 10 different instruments on them, the magnetometer, an optical, a thermal infrared. NISAR is a single instrument. It's just the radar. And it does a remarkable range of science. It enables a remarkable range of science, right? Everything from glaciology, looking at the dynamics of ice sheets and ice shelves, understanding the physics of the ice shelves, understanding where ice shelves are pinned on the bottom, understanding which ice streams are moving quickly or changing speed, all these questions about sea level rise. Looking at the ecosystems, looking at the change of the biomass, trying to understand where there's been deforestation, things like that. Looking at what happens in coastal areas, mangrove forests. Solid earth science, earthquakes, volcanoes, and so on. We're going to spend a lot of time talking about this and a variety of coastal processes. There's also a lot of applications, things that are very important for rapid response to disasters. We'll talk a little bit about that. So it's really one instrument to control them all, right? We can really do the Hobbit, right? Everybody understands that, right? We can really do all sorts of things. And so we're going to focus on solid earth deformation primarily because that's my bias and it's what I know most about. Okay, so when I talk about solid earth science, for me, that's earthquakes and the rest of the seismic cycle, what happens during earthquakes, what happens between earthquakes, what happens right after a big earthquake, volcanic processes, how does magma move in the subsurface, eventually leading to eruptions, landslides, identifying them, looking for changes in the landslide behavior, understanding the basic physics of what controls their speed up and slow down. All sorts of things to do with hydrology and ground subsidence. These are typically very linked, and in fact, they're linked to resource exploitation as well. Since when you drink water, you reduce the pressure in the aquifer and the surface will drop, and we can measure that, and that's what we'll talk about. Permafrost and all sorts of other things. Because of time, I won't have time to cover all of these things. I'm just going to pick and choose a few things. So most of what I'm going to talk about is really either a direct or a derived product from this thing called NISAR, Interferometric Synthetic Aperture Radar. It's going to be all examples using the existing international constellation of SAR satellites. There's a lot of SAR satellites up there right now that we can already do remarkable things with. So we're going to use those as motivation for approximately half this talk to understand this is the kind of things that we expect to be able to do, but even better, right? Once NISAR launches. Okay, so that covers what is NISAR. Let's go to our quick primer on INSAR. Okay, so whenever we do interferometry, the term interferometry by definition is one where we are actually combining two different kinds of measurement and looking how they interferometry, or how they interact with each other, right? It's a bit messy. I don't want to go into the details, but fundamentally, what it means is taking an image, coming back some other time, taking another image, and asking how do these two images change, but in a way which is unusual because we can actually measure the distance to the ground between the satellite and the surface in terms of units of wavelengths of the radar, right? So this is why I keep coming back and talking about radar wavelengths, because that's intrinsic to our measurement, right? And you come back a second time, you make another measurement, and you can actually take the difference between the two, and you can measure, let's say if there was an earthquake and the ground moved, or there was subsidence, or something else changed, a glacier flowed, you can actually measure the change in distance between the satellite and the ground with exquisite sensitivity. And you can measure this in the direction that the satellite is looking. For a variety of reasons, it turns out that the satellites always look to the side, the radar satellites, either the right side or the left side. And so we measure what we call the line of sight component of the ground displacement. So the ground can move in three dimensions. We live in a three-dimensional world, but we're only measuring that component, which is how much it moves in and along this line of sight direction. Of course, if you come back a second time or third time and a fourth time from a different viewing angle, you can get different line of sight views. And in some cases, you can actually reconstruct the full 3D or east, north, up ground motion for every pixel. And we'll talk about that in a second. All right, so the technique inherently depends on comparing pairs of radar images from two times. It can be months, days, in some cases, if you're on an airplane, hours. It provides measurement of how every pixel moved more or less independently from the pixel next door, right? You have images that are 100, in our case, probably around 250 kilometers in scale. Each pixel is meters in scale. That gives you some sense of the amount of data we're going to talk about. And we're getting sensitivity of a few millimeters of ground motion. So the ground moves just a little bit at every pixel, and we can measure that from space, okay? You can take hundreds of images and pair them in all sorts of combinatorial ways and make even more numbers of pairs, greater numbers of pairs. So you have all these pairs, and then you can combine them to basically make a movie of how the ground moving, a time series of how the ground moves in that line of sight direction. And then you can apply it to all these kinds of things that we've talked about. So fundamentally, you take one image. This is what it would look like if you looked at the amplitude of the image. I talked about phase. Don't worry about this as if it's new to you. But we have these two quantities. This is fundamentally what we're measuring the distance to the ground with. You wait a while. You take a second image. You have a big black box, which is known as JPL, or your computer, or something else. You stick the data in there, you do lots of physics, satellite orbits, signal processing, you worry about things like tides in the atmosphere, how to map things, and so on. And out comes two quantities. One is where does the measurement fall apart? That'll be useful in a second. And these coherent images of ground motion. So what does that look like? It looks something like this. Not only is it a nice tie-dye t-shirt pattern, but it turns out to be a contour map of how the ground moved, in this case, due to an earthquake, right? So each of these contours, you're used to looking at topographic maps. Instead of being contours of topography, this is contours of ground motion. In this particular example, this is from an earthquake that occurred in 1999, so almost a quarter century ago, called the Hector Mine earthquake up in the Mojave Desert of California, magnitude 7.1. And it's an image before and an image after the earthquake differenced, and you get this topographic map. Instead of topography now, it's a deformation map. Every color cycle here is about an inch in this example. It depends on the wavelength of the radar. Again, that wavelength comes back up. Each pixel, I tried to draw it, but there's no way of drawing it to scale. It's a meter scale pixel. This one is about 100 kilometers across. NISAR will be doing 240, 250 kilometers scale images, so more than 2.5 times the size. And it's kind of like if you had a GPS at every single pixel, tracking how every pixel moves, right? Except for we don't have to install the GPS, it's from space, and we can do this globally for all the subaerial portions of the globe. So that's everything I'm going to say about how INSAR works. Everything relies, this is one pair, on taking hundreds, thousands of these pairs, combining them appropriately to develop these movies of ground deformation. In some cases, here you can see everything gets really messed up close to where the rupture of the fault occurred. And that's an area where we would say they're decorrelated. It's where the measurement falls apart. And that itself is a useful measurement of devastation. And so when I talk about devastation, we'll talk about using that as a useful product as opposed to just an annoyance. As a geophysicist, it's irritating because it means we can't measure the ground move. An emergency responder would care about where this thing falls apart because that's where there's been lots of devastation. All right, so let's move on to our vignettes. The first example is going to be about the earthquake cycle problem. I thought I'd pick one from nearby. This is a San Andreas fault here. And when we think about earthquakes, you think about some chunk of ground from near the surface to some depth slipping very quickly over a few seconds to a minute. 10 minutes in the context of magnitude 9 earthquakes, seconds for small earthquakes. And the rest of the world behaving more or less like an elastic body. Between earthquakes, you have the opposite happening. You have slip at the faults at depth where they're not stick slipping, where they're actually just creeping along. And if you add a lot of earthquakes and a lot of interseismic period and you add them all up and you integrate over thousands of years, you end up with net motion in this cartoon of something like this. And this is sort of the gradual motion of the tectonic plates along the San Andreas. And that is what you're seeing here. This is like this picture. This is what would shake things up. And this is what happens in the time, in the hundreds of years between big earthquakes. And we're interested in looking at these parts of the cycle because it tells us which faults are actually accumulating stress that could at some point unpredictably eventually result in a large earthquake. So this example here is taken on the creeping section of the San Andreas Fault. So we have San Francisco up here. We have Southern California starting down here. The last big rupture was in 1857 down here. And the last big rupture up here was the 1906 earthquake. And there's two sections of this fault. There's the Calaveras Fault and the San Andreas Fault here. Okay. So I thought I'd show this comparison because it's kind of useful. This is using GPS. So each arrow is one station of the GPS and how it's moved over time. And you can see that this side is moving relative to this side, and that's the sort of the gradual motion of the Pacific relative to the North American plate. It's a lot of work that goes into developing one of these maps. Now, if you look over here, this is from a Japanese satellite. And so we have three orbital tracks of data. Each one of them involves tens to more of images. And you can see, by and large, there's this purple color on one side and this yellow-green color on the other side. And that's showing you the same thing that you're seeing with the GPS. And then you can combine these two kinds of data sets to actually develop a model or an understanding of what's happening in the subsurface, below the surface, on the fault, right? And so you can actually go through a whole process of, here we've cut up the fault that extends deep into the earth into little tiles and asked how much slip is happening on each tile continuously, so creeping along, that results in those observations at the surface from the GPS and the radar data. The red colors are slipping quickly. The blue colors are not slipping at all. This is where the 1906 rupture stopped. This is where the 1857 rupture stopped. And you can see it's consistent that the areas that are now currently stuck are the same areas where you had the big earthquakes in the past, will probably have big earthquakes in the future, and are currently locked, right? They're not creeping. Down below, you can see this thing is creeping. Here, it's a bit complicated because we have these two strands of the fault, and you really need to think about how this and this add up. We can't really resolve the difference between these two faults at depth. Right? So that's one example that we can not just do on the San Andreas. We can go globally and do this kind of problem, even if they don't have a GPS network. All right, so let's take another example here. Let's look at Iceland, one of my favorite places. So in Iceland here, we are sitting on the North Atlantic ridge where the North American plate separates from the European plate at about 2 centimeters a year across Iceland. And If you look at the age of the rocks, of the lavas, you can see that they're younger rocks shown in orange in the middle, and they age as you go away, and that's really because this is where the plates are spreading, and you're forming new plates in the middle. The whole thing gets moved out on the conveyor belt. New material comes up, so it's always young along the axis and gets older as you go away. That's 2 centimeters a year. It's this sort of 100-year average kind of number. The question is what actually happens, just like on earthquakes, it happens impulsively. Things happen in short periods of time and then nothing happens for a while. And what does it look like? It looks something like this. So this is the Barabunga eruption that occurred in 2014 underneath the big glacier. I'll show you a map in a second. I just like this picture. This is what it looked like afterwards. Walking on it. This is my wife for scale. She's fastened forward. She's got a Barbie pink hat. And these are what these eruptions look like. You get these big rift eruptions because it's really trying to fill in this long linear segment. They're quite dramatic. What does it look like from space? It looks something like this. This is a composite. So we're right here in the central part of Iceland. This white area is this big monster ice cap called Vatnajökull. And we have one interferogram, or radar data set, that was taken over a day interval at one radar frequency. It turned out to be X-band for the experts. And then another one that was taken over 24 days, C-band, so a different wavelength. The C-band data doesn't, over 24 days, falls apart and doesn't work on the ice. Very important. So we have no data here. The X-band data also doesn't work on a lot of the ice for related reasons. This data here, these concentric circles, are showing you dramatic collapse. It's actually dropping. It was, for a while there, at 50 centimeters a day, so 1.5 feet a day. It was dropping. The ice was dropping because of what was going on underneath the ice. Out here, what you're seeing is actually this contour map of the plates opening up, right? So you're watching plate tectonics in action here. So what does it look like here? This model that we derived for here is something like this. You have a magma chamber that is collapsing. That magma is evacuating from the magma chamber. It's propagating along. As you can see, these dots represent seismicity, so small earthquakes, propagating along. So this is emptying and eventually gets out from underneath the ice, so we can start to image it because it's on a basalt or lava surface and not under ice surface, and it works. And meanwhile, as it drops, the ice just falls along as a passive tracer. If you look at this part out here, you can play the same game we played on the San Andreas Fault, but here we're actually mapping. The color indicates how much it's opening, right? Because as you're forming new lithosphere, and you can see that over this 23-day period, it opened 6 meters or about 20 feet in a very short amount of time. I thought I'd just grab this for fun. This is taken from a couple weeks ago from the Icelandic website from their weather service. They're now producing interferograms at the weather service using the European satellites of this eruption that you've been reading about in the news for the last few weeks called Fagradalsfjall. And here you're seeing about 0.5 meter of opening over that time period associated with the rifting eruption there. Again, just think of these as contours of ground motion displacement. All right, next example, we're going to go to hydrology. We're going to look again here in Southern California in the Los Angeles basin. So here we have Palos Verdes, Pomona. We're sitting right here somewhere right now in Pasadena. And again, this is going to be the same kind of idea. We're going to take 165 images. We're going to pair them up in all sorts of different ways to make nearly 1,000 interferograms. And we're going to take those interferograms of those pairs, and we're going to turn it into a movie. And then we're going to take that movie, and we're going to separate it into short-term signals, short-term means seasonal, and long-term signals, which are the long-term evolution of the aquifer, which we'll talk about. So this is the short-term part. So this is actual data. This is not a model. And what you'll see is the axis here is plus or minus 3 centimeters a year, so a little over plus or minus an inch. You can see the entire aquifer is going up and down. This is the surface of the Earth. You know, it doesn't happen fast enough, so you don't feel it when you're out there. But it's actually doing this all the time, right? And it's because we drink the water, it fills up. We drink the water, it fills up seasonally, right? Now, of course, it turns out it's not in perfect balance. We tend to, not surprisingly, drink more than we let it fill up. And we'll look at that in a second. But I wanted to show you this thing. You'll notice that it goes up first in the middle and then up later. There's a delay. And so you can actually keep track of when does it hit its peak, right? And that's what's shown here. This is what we call phase delay. And you can see that it actually starts in the middle and then it propagates outwards. And you can see it in the movie. It starts in the middle and sort of ripples outwards. And that's really important for people who want to try to understand how the aquifer works. It's to track this phase delay and to track, where is the water getting to different places at different times. You'll notice that there's a cut right here and a very sharp boundary right here, right? The sharp boundary on the left is the Newport-Inglewood Fault. It's a very well-known fault. And in fact, it is so well mapped here, this phase delay is so well mapped, we can tell you within 100 feet or 50 meters, 30 meters, if you're on the aquifer or if you're off the aquifer, right? So it's really cool, just from the surface deformation. This other structure that is circled here is unknown. We don't know what geologic structure there is, so that's actually a target for us to go and look at eventually. That's something that we didn't expect. Now, of course, there's not just the seasonal signal. As I alluded to, there's long-term effects here. So this is over many years. And you can see that there's this long-term subsidence of the entire aquifer, right? That can be of two sources. One, that you're drinking more than you are refilling it. Or two, long-term changes in the elastic properties of the aquifer, right? You're actually destroying part of the aquifer's ability to retain water. In this case, it turns out it's probably just the imbalance between how much we drink and how much it fills up on a seasonal basis, right? Here you'll see this thing actually going up. That is not a mistake. That is an oil field, and they're actually injecting water in order to maintain the pressure of the oil field. And they're actually injecting slightly too much, so the pressure is going up and the ground is rising as a result. All right, I thought I'd show this example also from folks on the NISAR science team. This is a beautiful example of the Central Valley. So here you have the Sierra Nevada, here you have the Central Valley. Of course, right now there's Tulare Lake, which is probably covering half of this thing. But, and it's the same idea. The color represents when is the water hitting its peak. And so what you're watching is the effect of all the snowmelt in the Sierra propagating through the major rivers and starting to refill the aquifer in the Central Valley. So you can see it starts off on the eastern side, propagates through, it's coming out in a lot of these major river areas, and then eventually fills in the whole thing. So you can see that NISAR is going to be really important for studying shallow aquifers. I thought I'd show this example here, which I really like, from Saudi Arabia. So here we are in the Red Sea here. Here's the Arabian Shield. And we're just going to zoom in just to a smaller area here. We were originally interested in the tectonics of this area, but as a result of looking here, we actually saw this thing happening as well, and I thought that was kind of exciting. So here's what we saw here, that zoomed in box. You can see an area that is dropping 6 centimeters a year, and it has been doing so for a while, and it appears to be continuing to do so. This is 2014 approximately to 2022 approximately. This is that's at this triangle. You can see this color, and it's this sort of weird snake-like structure that is subsiding, right? And it turns out, my guess is that's an old paleo river, right? And this paleo river is now serving as the catchment, right? So the geometry of the river is controlling the aquifer, and then there's a very different behavior. On the right side, there's a basalt cap. There's a hard rock cap, and on the left side, it's just alluvium. So these two different areas behave very differently, right? Now you can ask a separate question, which is, if this continues, how long is it sustainable? And that's actually a very important question, because of course in this part of the world, aquifers are a huge source of water, and in many cases the water they're drinking is thousands of years old, right? And so that is clearly not being replenished. Furthermore, if you look at this area and you just look at the derivative or the gradient or the tilt implied by that amount of subsidence, it turns out it's all concentrated on the edges, not surprising, as this whole thing is dropping like this, so the big effects on the edges. And this is the same thing that's mapped here. And what's interesting is one of the primary oil pipelines that go from east to west Saudi Arabia crosses right through the middle of this thing. And then one of the major train lines goes up and just touches this. So you're starting to see a sense of this connection between, it's not just for science, not just for exploitation of resources, but also the impact of ground change on the built infrastructure can become very important as well. All right. The last vignette I had was about devastation. I'm skipping glaciology for lack of time. There's a huge need, especially in less developed nations, for information, for situational awareness. What just happened in the disaster? And earthquakes are particularly pernicious because they're unpredictable. Hurricanes, you have some time to prepare. And they can impact very large areas. They can destroy your communication infrastructure. And so then the whole business of understanding what just happened becomes very important. We started a project between campus and JPL over a decade ago called Arya, the Advanced Rapid Imaging and Analysis Project, which aims to think about how we use all the science that we do now and all these data sets for rapid use for societal benefit. So here's an example which I really like. It's an older example now. It goes back to 2011. This is from the Christchurch earthquake in 2011 in February, magnitude 6.3. And we've now gone and looking at all those contours where it gets messed up in the middle that we talked about at the beginning. That's what we've highlighted with these red pixels. These red pixels are areas, we call it damage proxy, but it's really devastation proxy. If you just shake the building, we're not going to know about it. If you flatten the building, we're going to know about it, right? And so this is why it's called, I call it a devastation proxy map, but people call it a damage proxy map. But they both start with D, so it's okay. And so this is the engineer's version of the damage that actually occurred in that earthquake that was done some months later. And you can start to see broadly the correlation of the big red areas with these, except for we have more, and we have much finer granularity. Turns out that's not noise, that's real. And you can, at the individual pixel level, you can start to see identified red pixels, and this is what it's looking at. And so you can see that there's a lot of promise for being able to use these techniques and newer versions of them, which I'll show you in a second, to assess damage quickly after an event, as long as you have the data available. We have to be honest. We are limited by orbital mechanics. We can go really fast once we have the data, but you do have to wait for the satellite to come over, right? And that may be days in some cases, and other times it may be hours, and that's just an inherent limitation depending on the size of the constellation. Here's an example from Kathmandu, from the Nepal earthquake, lots of yellow pixels because there was lots of damage all over the place. When we first got this image, we were like, what are all these things? Do we believe all of this damage on the mountaintops? It turns out they typically build their villages on the mountaintop. And all these purple dots are where folks that work in three-letter agencies using resources that we don't have access to actually identified individual buildings that had been destroyed. And we can see a very strong correlation between what we had identified. And you would not know about this in these areas for a long time normally, right? Because they're just hard to access to. In Kathmandu, there's lots of examples of actually chasing these down. So I think this and future versions of these technologies are going to be extremely important. We'll come back to that in a second. I want to show you another example here from the Ridgecrest earthquake. So before we looked over here for the creeping section of the San Andreas, the first example I showed you was from the Hector Mine earthquake over here. That was like the pretty tie-dye picture. And the Ridgecrest earthquake is up here north of the Garlock Fault, which is here. We had the Mojave going up to Mammoth and the Owens Valley up there. There were three major earthquakes, 6.4, 5.4, and 7.1 in a short amount of time. And then these are all the aftershocks from each of these, as well as the aftershocks from that also showing up over there. You get another one of these pictures here showing you the complexity of the faulting, right? Remarkably complicated beast. Strands of the fault here, strands of the fault here, here, and so on. And then here is this damage assessment shown for the fault. And actually, in this particular case, is a very precise mapping tool for where did it rupture, right? Of course, we were fortunate. This is an uninhabited area largely. There's a few towns. There's a town of Ridgecrest that got hit hard. Now, with machine learning techniques, we're getting actually a lot better at doing this. And we can actually ask for every single pixel. We can ask the question, how much is this pixel different from how I would have predicted this pixel to behave based on its history in the SAR time series, right? So we can do this long INSAR time series, doing lots and lots of analysis of each pixel independent of each other pixel, and ask how much more change has there been relative to what I would have predicted. And so I can get a confidence interval for how much or how devastated it is relative to its past behavior. So this is setting a fairly low threshold, lots of areas, large area that looks changed, and you can change with increasing confidence, or in other words, greater shaking. You can zoom in and actually identify different features. These are the actually shorelines of the local lake. And a lot of this relates to both the earthquake and how the ground responds to the earthquake. Is there liquefaction? Is there devastation? And so on. So it'll be interesting in the future to relate this to actual models of ground shaking. These damage proxy maps can be used for a variety of purposes. This is a nice example that was done as part of the Arya project, showing the evolution of the Bobcat fire in 2020. So here we are, Arcadia. We're sitting right over here somewhere right now. And you can see it, the area that is changing or decorrelated or devastated growing as a function of time. And in fact, there's all sorts of applications for these kinds of things. This is in Sulawesi, looking at the devastation from this earthquake. There's the fires we just looked at, tracing volcanic lava flows. This is that horrible explosion in Beirut in Lebanon, and how much it flattened large parts of the inner city. And you can actually see the tornado track going along here in the city. All right, so that ends my 3 vignettes. So why are we so excited about NISAR? I showed you a lot of examples, not all, that were at shorter wavelengths. I'm going to show you the example of comparing different wavelengths. But NISAR is L and S band. It has two frequencies, 2 wavelengths. It has multiple polarizations, just like with your camera when you change the polarization filter of your sunglasses. It has a very steady repeat. So every 12 days, you're going to see images from one orbital direction, and also every 12 days from the other orbital direction. So that gives us coverage approximately on average every 6 days. The swath is 240 kilometers wide. It's huge, right? And this sort of 10 to 100 meters per pixel resolution, it's a huge amount of data, 40 terabits of raw data per day, right? So it's a huge challenge to figure out how to actually take advantage of this opportunity, right? The data is free, open, theoretically easily accessible, and so we're very excited about that. So let's talk about that. Why do we care about L-band and S-band being so important? It means that you're less sensitive to the ground disruption. So I showed that example in Iceland where the data fell apart, and I'm going to show you some more examples in a second. The instrument's been designed to take care of a lot of the things which actually annoy us, like the effect of the atmosphere, propagation effects to the ionosphere, and the change in water vapor in the atmosphere. Our satellite actually looks left. You'd say, so. Left is important because all the rest of the constellation, the international constellation, looks right. What that means is we are actually measuring a different component of the displacement field, so we are complementary, and the 2 data sets can be used together. We have this consistent 12-day acquisition. It's really about the era of time series, right? Doing these time series is what allows us to separate overlapping processes based on their space-time behavior, a bit like I showed you for the LA aquifer going, the seasonal and the long-term effects. And you have this wide area mapping, which is really important for tectonic problems when you're looking at sort of plate scale movement. So let's see this example. This is also from Eric Fielding on our science team. You see the example of C-band, so that's a 5 centimeter wavelength, versus L-band taken from the Japanese example here. This is 12 days, this is 8 months separating the 2 images. So there's a lot more time for things to change in addition to the earthquake that you're looking at. You can see there's huge areas where either due to vegetation and large deformation and decorrelation that you're not able to measure. Here you can get much closer to the fault. The displacements increase as you get closer to the fault, which is why, by the way, these scale bars are not the same. And you can see a lot more of the important geophysical signal. Another example also taken from our group, from Zhonglu, from the NISAR science team, an example over Hawaii, showing what's going on in the rift zone. And you can see if you look in C-band data, the whole thing falls apart due to vegetation. And you can look at L-band data, and you get these beautiful maps of ground deformation, okay? You'll notice this pattern looks a lot like what we saw for the most recent Iceland event, just tilted. It's again this separation and fault motion. So other examples also from Shu et al. Also shows tracking landslides. If you look at optical data, especially in vegetated areas like in the Pacific Northwest, you could not tell me that there was a landslide there. You would not know. And yet when you look at the radar data, at L-band data that is less sensitive to the vegetation, you can map out the actual motion of the landslide. You're not actually detecting the structure of the landslide. You're detecting what is moving and therefore the boundaries of the landslide. And you can see these landslides nicely mapped. So it can be very, very important for landslide mapping. I mentioned the propagation to the atmosphere. This is kind of fun. So here's an aurora in Iceland. It has two effects. One of them, this decorrelation or the noise that we talk about. If you have a lot of ionospheric activity, it can actually cause problems in this decorrelation. But also it can give you apparent motion, which is not real motion, right? So it would confuse you. NISAR is designed specifically with the ability to remove the effect of the ionosphere from the data itself. I'll skip you the details, but here's an example of an original pair, 1 interferogram, estimating the effect of the ionosphere from the data. This is all due to the ionosphere, and this is what's left, right? This turns out to be a beautiful representation of what happens. This is taken from this track, and it's what happens due to an 8.8 earthquake in southern Chile in the Maule earthquake, right? You would never see this beautiful pattern if you were struggling with this kind of observations, right? And NISAR is taking advantage of our 2.5 decades of experience to really build in some of the ability to remove these kinds of effects. NISAR will produce global coverage. So the entire solid sort of subaerial part of the planet will be covered every 12 days, ascending every 12 days, descending. There's different modes. For the solid Earth folks, basically we get everything that we want over this whole map every 12 days. Because it's left-looking, it turns out it can see all of Antarctica. That makes it very complementary to the existing constellations, which have a big hole over Antarctica, right? So very important for studying Antarctic cryosphere questions. So a bit of a rogues gallery. This is that reflector antenna as it was being deployed and tested. This is at JPL. This is now the reflector antenna totally bundled and shut. And this is how it's being slowly put together, tested for thermal effects and vibration effects and things like that. Whoops. This is as it's getting ready to get shipped to India because it's being put together in India and then being launched on an Indian rocket. This is actually on its way to India. It just barely fits in the C-17. And these are folks very excited when it got to India. Okay, I thought I'd end with a movie. Paul's not here, right? So this movie is put together by our leader, Paul Rosen, who is officially the director and producer of this movie. So he deserves an Emmy or an Academy Award. So this is the launch and deployment sequence that we are hoping to have happen in less than a year. Very important. Without solar panels, you're kind of in trouble. I'm sure Paul would have appreciated that. That reflector is 12 meters, almost 40 feet in diameter. Okay, it's really a big structure. And that boom, how big is the boom?
9 meters.
9 meters, so it's a 30-foot long boom with this thing attached to it. All right, so hopefully I've convinced you that we are in the golden age of satellite remote sensing. Not only is there this remarkable international constellation that exists, that's continuing to be built by our international partners, but NISAR is going to contribute a whole different component to that observing ability. It's going to allow us to measure things that we could not measure before, and then complement the measurements that already exist. The data will be easily accessible. Tools for analyzing the data, for downloading, with playing with the data, low-level processing, high already very processed data will all be available for people to play with depending on your desires. If you're interested in learning more, there is a handbook that introduces you to the measurement and the kinds of applications and the things we've talked about. You can go to the NISAR website, nisar.jpl.nasa.gov. You can go download this handbook. It's very helpful. We launch, hopefully, late winter, early spring next year. It's less than a year. And for those of us who've been waiting for 30 years, it's kind of remarkable. I think that's it, and I'm happy to take questions.